With the concepts of probability and odds in our toolbox, we'll develop a new type of regression model called a logistic regression model that can describe binary responses. To develop ideas, we'll continue to look at our dataset of O-ring failures and outside temperature. Recall that our research question involved investigating the relationship between outside temperature and the chance of an O-ring being broken. To motivate ideas, let's look at box plots of temperature among O-rings that were not broken and were broken. We can clearly see from this plot that broken O-rings tended to occur at lower temperatures, which was a main point from our previous video. Given that we're shifting to view the binary broken variable as our response variable, we can try to change our plot to see if a linear regression model might be appropriate. Here we plot both variables using a scatter plot. Even though the broken variable is binary, we can treat it as a quantitative variable that happens to only take the two values 0 and 1. In so doing, we can fit a simple linear regression model of broken as a function of temperature. The linear regression trend line is shown in blue. Pause the video for a minute here, and based on this plot, reflect on what might not make this linear regression model ideal. Okay, we're back. Let's talk about that idea together. We can see that this trend line does roughly capture the idea that O-rings are more likely to fail at lower temperatures. But we have a problem. The line certainly dips below 0, even within our observed range of temperatures. So even without extrapolating, it's possible for this linear regression model to give us predictions that don't make sense. In order to understand how to improve this linear regression model, let's take a closer look at what it is actually describing. The simple linear regression model that we just saw can be written as shown here, where the response variable y is the broken variable and the predictor x is temperature. The left-hand side is the expected value of y, or in other words, the average value of y. For quantitative response variables, the idea of an average value of y makes sense. It's an average price, an average weight, an average salary, or whatever the response variable is. What does the average value of a binary response variable mean? It actually turns out that the average value of a binary variable is the probability that the variable equals 1. To see why, let's look at an example. Say that we had 5 cases where 3 cases had y equals 0 and 2 had y equals 1. The probability that y equals 1 is 2 out of 5 because there are 2 1s in the 5 cases. This also happens to be the average of the y values because the sum of the 0s and 1s is 2, and there are 5 observations. So linear regression models used on binary response variables are saying that we would like to model the probability of y equals 1 using the model on the right-hand side of the formula. The problem with this, as we saw on the plot just before this, is that predictions can go beyond 0 and 1. And because probabilities can only range from 0 to 1, this doesn't make sense. Ideally, we'd like to transform what is modeled on the left-hand side so that the predictions for this transformed quantity can be any number. We've seen that probability on the left-hand side is no good, but what about odds? Using odds is also no good because odds can only range from 0 to infinity. Since odds are the ratio of two probabilities, which are both positive numbers, the result can't be negative. Let's try one more idea. How about the natural logarithm of the odds? So this will actually work. The natural logarithm of an odds can be any number, which is what we wanted. So let's review some key ideas related to natural logarithms to help with this idea. A graph of the natural logarithm function is shown here. On the horizontal axis, the odds range from 0 upwards, and the natural logarithm of the odds is plotted on the vertical axis. We can see that when the odds are quite small, the natural logarithm is negative. And as odds increase, the natural logarithm of the odds also increases into the positive numbers. If we have a log odds value and we want to obtain the odds, essentially going from the vertical to the horizontal axis, we can exponentiate the log odds. For example, say log odds is equal to 0. We can obtain the odds by exponentiating 0 using e to the 0, and this is equal to 1. So let's come back to the model that we proposed. This model, where we modeled the log odds on the left-hand side of the formula and a line on the right-hand side, is called a simple logistic regression model. Just as in simple linear regression, the simple part comes from the fact that only one predictor, x, is present. This model tells us that a form of the chance of y equaling 1, that form being the log odds of y equaling 1, depends on x in a linear fashion. So for our O-ring data, we would write the model as shown here. The log odds of broken being equal to 1, which in this context means the log odds of an O-ring being broken, depends on temperature with slope beta 1. We can interpret the slope as we have before with simple linear regression. Beta 1 is the change in log odds of O-ring failure per 1 degree increase in temperature. Based on our previous investigations, we would expect beta 1 to be negative because the O-rings were less likely to fail at higher temperatures. So note that the on-average part of the interpretation that was present for linear regression models is automatically embedded in the meaning of odds. So here we can omit saying on average. We described the interpretation of the logistic regression coefficient beta 1 as a change in log odds per degree increase in temperature. There's actually a special mathematical property of logarithms that makes for a special interpretation of this coefficient once it's exponentiated. So when we describe a change in log odds, we are describing the difference in the log odds of an O-ring being broken when the temperature is T and when the temperature is T plus 1. It's actually a special property of logarithms that the difference between two logarithms is the logarithm of the ratio. In other words, this difference in log odds is actually the natural logarithm of the ratio of those two odds. This means that e to the beta 1 gives the ratio of the two odds. In other words, e to the beta 1, the exponentiated coefficient, gives the multiplicative change in odds per degree increase in temperature. So it so happens that when we fit this model in R, the exponentiated coefficient ends up being 0.89, which we can interpret as such. For every 1 degree Fahrenheit increase in temperature, the odds of an O-ring being broken is multiplied by 0.89. In other words, the odds and probability of an O-ring breaking decreases with increasing temperature. Going beyond our O-ring data, logistic regression models are more broadly useful in many settings, one important setting being public health. So for example, logistic regression models can be used to understand risk factors for a disease in a model such as this. Here, the log odds of having a disease is predicted by multiple predictors, age, and family history. We'll see that the concepts of model building and output interpretation that we developed for linear regression models will continue to apply for logistic regression models.